Elements are the building blocks of all life on Earth. One metal that is often overlooked but is very important for biological functions is iron. Since both humans and bacteria need this iron wars have broken out and each side has developed biological weapons to survive. Enter to the scene lactoferrin, a protein that has an extremely high binding affinity for iron 3 ions. Lactoferrin is a member of the transferrin family, which is a group of proteins that bind specifically to iron. Transferrin has a lower binding affinity to iron than lactoferrin does, and a slight dip below biological pH can trigger the protein to release its ion. This makes it useful to transport iron since it can bind and easily release the ion, but it is not as effective at fighting off bacteria. Lactoferrin, on the other hand, can bind to iron until pH drops to around 2 to 3, which is very acidic for the body. Acidity this low can be found in inflammation sites, cellular vesicles, or in the stomach, but not in most bacteria. Lactoferrin's ability to hold on to iron so well makes it a great tool for the iron war, and its unusually high binding affinity is rooted in its structure. Lactoferrin has two hemispheres, the N-terminal and the C-terminal, which are connected by an alpha helix. The alpha helix is unique to lactoferrin within the transferrin family, and is more rigid compared to the simple linker found in other transferrin proteins. Researchers speculate that this inflexibility is part of the reason why lactoferrin retains its ions so well. Within each terminal are two lobes, with a cleft between them where the metal binding site is located. The amino acids found at the binding site are the same in all transferrin proteins. These binding atoms consist of two phenolate oxygens from two tyrosines, a histidine, an aspartic acid, and a carbonate ion bound to an arginine group. Researchers predict that the carbonate ion is the first to bind to the iron, followed by the two phenolate oxygens from the tyrosine groups. Then lactoferrin undergoes a conformational change wherein the N-terminal closes like a hinge to lock the iron into place. The resulting structure brings the iron closer to the histidine and the aspartic acid found at the binding site. The final structure that forms is very stable and protects the body from potential bacterial invasion by preventing any free ions from being in the environment where bacteria could be found. The specificity of iron to lactoferrin can be explained through a variety of inorganic concepts. Let's start with the chelate effect. The chelate effect states that as the number of individual molecules in a system increases, so does the stability of a complex. The free iron ion is likely bound to 6 individual molecules while free in the body, but when it binds to lactoferrin, the number of complexes goes from 2 to 7. Another important contributor to iron selectivity and stability is hard-soft acid-base theory. This follows the idea that like binds with like. Iron 3 is a hard acid, and all of the binding atoms in the amino acids bound to iron 3 are hard bases, with the exception of histidine. This makes the resulting complex very stable. Finally, another contributor to molecular stability is the geometry of the metal binding site. When a metal binds to a ligand, it can form bonding and antibonding orbitals for electrons to occupy. When this difference is small, the system is said to have a weak field, and the electrons are high spin, which means they will occupy the higher energy orbitals before pairing up with each other. On the other hand, when this difference is large, the system has a strong field, and the electrons are low spin, so they will pair up before occupying a higher orbital. When bound to lactoferrin, iron 3 has a weak field, so its d electrons will occupy the higher energy orbitals and won't pair up. Ligand field stabilization energy can determine the preferred geometry of an ion. The LFSE for iron 3 is 0, which means there is no other ligand position that would provide a lower energy. Therefore, sterics rule. Usually D5 metal ions form an octahedral complex when bound to 6 ligands, since the bond angles provide the least steric hindrance. However, in the case of lactoferrin, the carbonate ion skews the geometry, which results in a distorted octahedral configuration. Despite lactoferrin's high affinity for iron, the iron wars are not over. Some bacteria, such as Enterococci, have developed tactics to fight against iron-sequestering proteins, including lactoferrin. These tactics include the use of siderophores, ferric reduction, and proteases that can cleave iron-chelating proteins. While bacteria use these defenses to regain some iron ions, these methods might shed some light on how the human body regains iron from lactoferrin. To date, this mechanism remains elusive, and it is unclear exactly how the body removes ferric iron from lactoferrin. Lactoferrin exists almost exclusively in secreted fluids, and is not known to be used for any other reasons than lowering iron concentration. The exception to this is with young infants. Lactoferrin is found in high concentrations in breast milk, and it is known that lactoferrin can be a source of iron for both the nursing infant and the mother. However, further research is needed to understand how this occurs. Lactoferrin is a very important protein for the body, and its fight against bacteria keeps you from getting sick every day.